Hi everybody, welcome to this lecture on automatic programming with genetic programming and grammatical evolution. Today we are going to discuss a radical idea, that is, making the computers write programs, or in other words, automatic programming of computers. While computers have done a great job in solving our problems over the last nearly 100 years, it has typically required a human being to write computer programs and the intelligent logic behind those programs. However, in this lecture, I am going to introduce you to some methods, namely genetic programming and grammatical evolution, that can write computer programs automatically. This is not to say that these methods can produce any program of any quality just yet, but even their early applications have already generated a lot of interesting applications. Both these methods rely on principles of natural evolution and rely on simulated evolutionary processes like genetic algorithm. But first of all, let me introduce you to the decades old dream of automatic programming. Programming is a process. No wonder thousands of universities around the world teach computer science or the art of computer programming. Hence, automatic programming has been an old dream, and at different stages of computer technology, automatic programming has meant different things. Back in 1940s, the computer programs were represented via holes on paper tapes. So when a machine was invented that could punch holes in the paper tape, it was considered automatic programming. Imagine the excitement at the time. But as the problems that the computers solved got more complex, we needed far friendlier ways of writing the programs. So early programs were written as binary code or their hexadecimal equivalents. At least that was better than punching code or punching holes. So perhaps that was automatic programming. But as humans, we do not think in terms of pure numbers. We think in terms of languages we speak. So along came assembly language. This resembled English. Now, because the computer's hardware cannot understand English, assemblers were invented to convert the assembly language programs into executable code. The process of this translation from assembly language to numerical code was seen as automatic programming. But programming in assembly language is nowhere near as easy as writing programs in modern languages like Python and Java. Hence, high-level languages were invented like C, C++, Java, Python, and eventually R. Each language required a compiler to translate their code into machine language or in the form that the hardware can understand. Hence, compilers became the state of the art in automatic programming. Also, some of these languages brought click and play features to add visual elements to our programs, like Windows, where the programmer didn't have to write any code. Instead, a fixed piece of code corresponding to these windowing elements was generated automatically behind the scenes. Some other modern examples of automatic programming are UML or Unifying Modeling Language diagrams, where the programmer draws the skeleton of their functionality via some tools. And once this visual skeleton has been created, the skeleton code is generated automatically behind the scenes. We call it skeleton code because it does not implement the core functionality, but only produces basic functionality like a function's name and the list of parameters. The intelligent logic, essentially the core functionality, is then filled in by the human programmer. However, lately advancements in the fields of program synthesis and artificial intelligence has also started to provide the actual functionality. So next, we see an example. This example comes from Microsoft Excel that provides a feature called flash fill. Flash fill is useful for formatting or cleaning the data so that it is ready for some subsequent analysis. Essentially, when the data is collected in the raw form, it may not be ready for analysis. So we need to format it in a certain way first. FlashFill can automate this formatting or cleaning by learning from an example that a human user provides. This means FlashFill learns the actions that the human takes on a piece of data and then repeats those actions on the remaining data. For instance, in this example, we are going to have a data column called full name, and we want to reformat the names as last name, first name. So we provide one example of this action manually, and FlashFill learns from that example and then behind the scenes generates the code automatically. Once that code is automatically produced, FlashFill executes this code to similarly format other names in the column automatically. This work uses techniques from a branch of computer science called program synthesis. Now, people with a background in machine learning and genetic algorithms can very well appreciate the importance of learning from examples or data. Hence, the radical idea is that if computers can learn machine learning models with examples given in the form of input-output pairs, they can also similarly learn computer programs. Just like a candidate machine learning model is evaluated based on how well it matches the desired set of outputs given a set of inputs, an automatically produced computer program can be similarly evaluated. However, the question is, what learning mechanism or learning algorithm can we use to automatically produce computer programs? Another related question is, how do we execute these candidate programs that we are generating by hundreds or by thousands? This in turn leads to another question, and that is, how do we even represent these programs such that the learning algorithm can easily manipulate and improve upon them as the learning goes on? Remember, the learning process of a learning algorithm can be quite different to how humans learn. So, understanding the representation is very important. Now, in this lecture, the learning algorithm will borrow inspiration from natural evolution. Hence, the learning algorithm in spirit will be a genetic algorithm. Let us consider an example task. Suppose we get a bunch of data in the form of input-output pairs. So the input is a variable x that can take various values, and correspondingly, the output is also a set of values. Now we need to produce a readable program that can effectively model this input-output relationship. The relationship is shown in this figure on your screens. So our objective function in this case is to produce such a program that produces output values that are very close to the desired output values or the ideal output values. So essentially, we have to find a function f of x such that the sum of squared errors between its outputs and the ideal outputs is minimal. Now, those who are familiar with genetic algorithms know that genetic algorithms evolve a population of solutions, and that genetic algorithms use genetic operators like crossover and mutation to evolve the solutions. Now, the question is, how do those mechanisms of crossover and mutation work for evolving computer programs? So suppose two candidate solutions that genetic algorithms produce are x plus sine of x and x minus 2 times x. Now if we conduct a one-point crossover, we randomly select a crossover point. So in this case, that crossover point is represented by this red dotted line. And thus we choose an example location. And as happens in a one-point crossover in a standard genetic algorithm, we simply swap the right-hand sides. As we can see, this generates illegal or syntactically incorrect solutions. If you want to convince yourself, just pause the video here and stare at these expressions. Therefore, representing programs in the same way as we normally write them will not work if we want to produce programs automatically. We definitely need to represent the programs in some other manner. Now, evolving programs has been so different to evolving solutions to other problems that this automatic programming via genetic algorithms has become an independent field of study in its own right. And it is called genetic programming, or GP. GP has employed or even introduced various representations for evolving programs. However, by far the most popular representation has been what are called abstract syntax trees. So instead of using the standard array-like structures for representing solutions as in a standard genetic algorithm, GP uses tree structures to represent the evolving programs. So how can we rewrite or represent program expressions via trees? So in this case, suppose we have an expression called x plus 4 times y. Okay, so the question is, how are we going to represent it as a tree? First of all, we will organize the program expression in the order of operator precedence. Since here we have a mathematical expression, we can go back to our classes on arithmetics that taught us that multiplication takes precedence over addition. So we can make that precedence clear by putting brackets around the operators that need to be executed first. Hence, x plus 4 times y can be written as x plus 4 times y in brackets. Then we can put the brackets around the whole expression. Now notice that bracketing presents the expression as a value or a variable followed by an operator such as a plus or multiplication followed by a value. For example, we have x, that is a variable, then an operator plus, and then a value, that is 4 times y. Now 4 times y is a nested expression, and it itself is arranged as a value 4 followed by an operator multiplication and then a value that is represented by a variable y. Once we have this structure, we can rewrite it as a tree. So we start with the least nested operator, that is a plus, and create the first node or the root node of our tree. Okay. Then we extend the left branch of the root node and put x there. So x is the branch hanging out of the top level node, that is plus. Question is, what appears on the right side of the plus node at the top? Notice the right side of plus is a whole expression, that is 4 multiplied by y. As before, we select the operator, that is a multiplication, and make it the right side node under the plus node. Now we extend underneath the multiplication node. So 4 appears on the left side of the multiplication node and y appears on the right side of the multiplication node. Here's another example. For loops are quite common in programming languages. So we choose an example from Java programming language. This for loop begins by setting a variable I to be equal to 0. Then it sets a limit that the loop will execute as long as I is less than 10. And in each iteration, I will increment via a plus plus operator. So we can similarly create an abstract syntax tree for this for loop. Our least nested operator now is for. So for becomes the root node. Now for requires three arguments to work with: a variable initialization, a limiting condition, and an increment statement. Hence we extend three branches from the root node. For the leftmost branch, we produce a subtree. As before, we put the operator that is the assignment or equals operator. We put I to the left of equals and 0 to the right of equals. Likewise, we create a subtree for the limiting condition. And finally, we write the increment statement with the increment operator on top and I variable underneath it. Now, those who understand genetic algorithms also understand that genetic algorithms create an initial population randomly. Likewise, GP produces its initial population, but this initial population is a population of trees. And these trees have to be generated randomly. But what kind of trees can it produce? For that, we must first list the ingredients. Much like the operators that we showed in the previous slide, we should define a set of operators or functions that GP can choose from. So suppose if we want to only evolve arithmetic expressions, the function set includes plus, minus, multiply, and divide. If we want to produce trees that can use if conditions, like most programs do, then we can include the if operator in the function set as well. Notice if will have three branches extending underneath it, just like the for operator in the previous slide. Now, programs and their trees cannot be built simply with functions. After all, functions need arguments. Sometimes these arguments can be supplied by outputs produced by other functions. But simply adding more and more functions as branches under the previously used functions in a tree will keep extending the tree indefinitely. So we also need some elements that can stop extending the trees. These elements are called terminals or the terminal symbols. The examples of terminals are input variables like x, y, and z, or constants like 1.0 or 2.3, or even other functions that require no inputs or no arguments. For example, if you are evolving a game-playing agent, a function that simply fires a bullet without considering any input will act as a terminal. Whenever we place a terminal in a node, the tree cannot grow any further. You can go back to the last slide to verify that. So whenever we use GP to solve any problem via automatic programming, we must specify the functions and the terminal set at the start. So now we have answered two major questions. First, how do we represent programs in GP? So as we've discussed, it's normally via abstract syntax trees. Next, how do we specify the ingredients of these trees? And the answer to that is, it is via functions and the terminal set. However, remember, our problem was that we want to do crossover in GP such that crossover does not produce illegal or syntactically invalid programs. So the question in your minds can be, have we achieved that now? Will crossover be trouble-free now? Let's examine that. Instead of using the standard one-point crossover, GP uses what is called a subtree crossover. So suppose we have two trees here. The one on the left is a mixture of an arithmetic expression and an if less than else expression from a program. Okay, so this IFLTE operator basically mimics the if less than else behavior. So this equals, if y is less than x, then return 3.2, else return 0.4. So this is expressed as a function if LTE that takes 4 inputs, and its tree can be easily drawn. So in this case, this if LTE is embedded in a larger tree that is on the left side. Likewise, there's another tree on the right side. And now we have to do a subtree crossover. So for that, we randomly select 2 nodes, one from each tree. Sorry for the interruption. Then we remove the subtree located under the crossover point in the left tree and swap in the copy of the subtree located under the crossover point from the other tree. Swapping subtrees like that produces no syntactic problems under certain conditions. Thus, tree representation and subtree crossover are extremely common in genetic programming. Later on, we shall show one subtree crossover can fail as well, but before that, let's see how mutation works in tree structures. As with crossover, mutation first selects a node as a mutation point. Then the tree rooted under that node is excised, and a randomly generated subtree replaces the excised part. So if you've digested all of that, here are some exercise questions for you to refresh your memories and maximize your understanding. First off, draw the abstract syntax trees for the given expressions in question 1. Remember to first group into brackets using the precedence rules. If 2 operators have the same precedence, for example, there are 2 plus operators appearing in expression 1, then the operator that appears on the left side gets the precedence. Also, when drawing the trees for if condition, remember to extend 3 branches underneath the node containing if function. For question 2, you have to cross the first 2 trees from question 1 such that one of the offspring produces an expression shown on your screen. For question 3, produce a crossover that produces a tree structure that evaluates to 0.0. For question 4, produce a tree that can generate illegal numerical values, that is NaN values. A hint is that you can cross the tree for the second expression with itself. And the second hint is that log of values 0 or below is undefined. Finally, for question 5, leave your comments below as to whether trees can grow or shrink in sizes as a result of applying subtree crossover and subtree mutation. If it happens so, what problems do you think can it cause for program evolution? We'll wrap up this lecture by discussing a potential problem with subtree mutation crossover. Remember, earlier we said that subtree operators do not produce illegal program expressions. Well, that happens if the output of every node inside the trees that we consider is admissible as input to every other node. Then we can randomly swap subtrees. However, this is not the case when a program contains multiple data types or contains expressions that have very different roles. For example, if we cross 2 trees corresponding to the 2 for loops, problems can arise. We cannot swap the subtrees rooted at the selected crossover points. This is because the role or type of the 2 subtrees is very different. The one on the left is an assignment operator, and the one on the right is a limiting expression. One cannot be swapped with another. So how do we handle such situations? That is the topic of the subsequent lecture on grammatical evolution. But until then, please review this lecture, attempt all the exercise questions, and leave your comments and discussions in the comments section below. Thank you for watching.